Okay, we are in section 2.4 now, and we're talking about exact equations. So just to summarize the last two sections, 2.2 and 2.3, we talked about separable equations and linear equations. And when you're looking at a first-order equation of either of those types, we have a specific solution method that works. We have separation of variables in the case of a separable equation, and then we have integrating factors in the case of a linear equation. But there's lots more first-order equations out there. Plenty more that aren't necessarily separable or linear, and so we're going to continue trying to develop techniques for solving the different kinds of equations we might encounter. Now, this section is going to deal with a type of DE that we call exact, and they don't occur that often. There's kind of a strict criteria that they have to meet in order to be called exact, and we're going to talk about that here at the beginning. I'll also say, before we get into this, even though Calculus 3 is not a prerequisite for this course, it's going to help a lot if you've had Calculus 3, specifically in this section. And the reason for that is because we're going to be talking about some concepts that come from Calculus 3, in particular the idea of a differential of a two-variable function, which we're going to define here at the very beginning. This is something that in Calculus 3 you typically talk about right after you introduce the concept of a tangent plane to a surface. If you're interested in learning more about that, I do have a Calculus 3 playlist on my YouTube channel. You can go check that out. But it's not necessary. You'll learn everything you need to know in this section here. So that's enough of that. Let's get into it. Let's suppose we have a function f of xy, two-variable function. This is a matter of definition. We define the differential of this function f, which we call df, to be the partial of f with respect to x times the differential dx plus the partial of f with respect to y times the differential dy. Because this is not a Calculus 3 class, I'm not going to give you any reasoning or motivation for why this is defined the way that it is, but it is defined this way for good reason, and again, you talk about that in Calculus 3. Right now, we just need this as a definition. Okay? Now, let's suppose that we're looking at a specific case where f of xy is a constant function, f of xy equals c for some constant c. Then the differential df is going to equal 0. And so setting df equal to 0 here, we get this special case. Partial of f with respect to x dx plus partial of y with respect to y dy equals 0. Okay? Now, these two partial derivatives here, remember, they are partial derivatives of a two-variable function, so they in themselves are also two-variable functions. And in this section, I'm going to be giving them different labels. So this first one, partial of f with respect to x, I'm going to relabel that m of xy. And then the second partial here, partial of f with respect to y, I'm going to call that n of xy. Okay, so looking at the left-hand side of this equation and making those replacements, m and n, in place of those partial derivatives, this expression here is what we call an exact differential. Okay, and the key thing here that makes it an exact differential is that this function is, both of these functions are partial derivatives of the same function f. This one is the partial of f with respect to x. This is the partial of f with respect to y. If that's the case, then we call that an exact differential. If it's set equal to 0, like we have down here, that would correspond to this equation up here. We call that an exact equation. Okay. Now, there's a couple of things that we do when we encounter an equation like this. First of all, notice that exact equations are differential equations that are put in differential form. We introduced differential form back in chapter 1, and I had mentioned back then that we talk about differential form because there are some solution techniques that take advantage of that form, and this is our first main example. This equation being in differential form allows us to do what we're about to do. So, given just any first order DE in differential form like this one thing that we would want to be able to do is determine whether or not it's an exact equation. And remember, m and n aren't just any functions of two variables. They're very specifically defined. To say that this is exact, once again, is to say that there is some other function, f of x, y, that these two functions are partial derivatives of. So to show that this is exact, one way would be to find a two-variable function that each of these is a partial derivative of. This is the partial with respect to x, that's the partial with respect to y. Finding that function is doable, but there's actually a faster way to determine whether or not these two things are, or whether or not this equation is exact. So using the way that we define m and n down here, and using a theorem from Calculus 3 called Clarins Theorem, which I'll show where it's used in this derivation, we can derive a test for checking whether or not a first-order dE in differential form is exact. Take your function m, and let's look at the partial derivative of m with respect to y now. Remember, m itself is already a partial derivative. It's a partial derivative of this unknown function f with respect to x. So then taking the partial of that with respect to y, that gives us a second order partial derivative. It's the partial of f with respect to x, and then differentiated again with respect to y. The notation that we use for this second order derivative is this: partial of f, and then down here, we read this from right to left to give us the order in which we did the differentiation. We differentiate with respect to x first, and then with respect to y. Getting from this step to this step is where we use this thing called Clarins Theorem. Notice what's happening is these two terms down here are switching places. Partial of x, partial of we have an x here and a y here, as opposed to a y here and an x here. If you're not used to working with partial derivatives, that may not look like much happened right there, but that's actually a very big deal that we can do that. We can only do that if these first-order derivatives are, if m and n have continuous first-order derivatives. That's what allows us to use Clarins Theorem in the first place, specifically continuous first-order derivatives on some rectangular region. That's what this whole setup here is talking about. But these things are called mixed partials because we're differentiating with respect to different variables, x and then y here, y and then x here. Clarins Theorem says that if you take a function that satisfies this criteria up here, differentiate it with respect to x, and then differentiate it with respect to y, and then if you take the same function and do that differentiation in reverse order, you'll get the same thing. Okay, so that's basically what this step is saying. But this is the same thing as the partial with respect to x of the partial derivative of f with respect to y, and this thing in parentheses is the same thing as the function n, and so this reduces to the partial of n with respect to x. Now what was all that? What did we just do? Well, following this through, if this expression up here is an exact differential, or if said differently, if this thing up here is an exact equation, then this equality would have to be true. Getting rid of all these steps in the middle, this equation is exact only if the partial of m with respect to y is equal to the partial of n with respect to x. Okay? In fact, we can say that using the terms if and only if. This is exact if and only if this little equation holds. Okay? So I'm going to use the examples to illustrate how we use this. All right. Here is a differential equation that may or may not be exact. We have to determine that. The function here is playing the role of m, and the function here is playing the role of n. Okay, so m is equal to x cubed plus y cubed, n is equal to 3xy squared. According to that criteria that we just derived, if this thing is going to be exact, then the partial of m with respect to y should be equal to the partial of n with respect to x. But what is the partial derivative of m with respect to y? Well, remember, with partial derivatives, if I'm differentiating with respect to y, then any x is treated like a constant. So that x cubed is going to go away. This becomes 3y squared. However, notice that is the same thing as the partial of n with respect to x. Because if I take the function n and I differentiate with respect to x instead of y, I'm treating y squared like a constant this time. And so this is like a linear function. Its derivative would just be 3y squared, same thing I got there. So this is exact. Okay? Now what is the point of knowing that this is exact? Well, let's go back here for a second and kind of work things backwards all the way up here. If we know that this is an exact equation, then that implies that there's some function f of x, y that these two guys are partial derivatives of. But where did we get this equation in the first place? We were looking at a special case up here where that same function f of x, y was equal to a constant. Notice that this function is a function of x and y only, not y prime or anything like that. And because that's set equal to a constant, this is actually an implicit function here. That implicit function or family of functions, because c is acting as a parameter, would be the solution to this dE down here. So our goal is to determine what that f of x, y is, set it equal to an arbitrary constant c, and we have an implicit solution. In other words, if this is m and this is n, and remember m is the partial of that unknown function f with respect to x, and n is the partial with respect to y, I need to figure out what function works for these two things here. So once again, m of xy, that's the partial derivative of our unknown function f with respect to x. So that would mean that f of xy is equal to the antiderivative of this thing with respect to x. There's more I'm going to write here, but think about this for a second. If you've had Calculus 3, you shouldn't be uncomfortable with an integral that looks like this. If you hadn't had Calculus 3 yet, you might be a little unsure how we integrate a two-variable function with respect to x. And it's basically the same idea as a partial derivative. In fact, we even call these things partial integrals. I'm integrating this function, but I'm treating any y's that are appearing in there as a constant, and I'm only integrating with respect to the variable x. Now, normally when you take an indefinite integral, you pick up a constant of integration. But remember, because we are integrating with respect to x here, and the y's are being treated like constants, instead of a constant of integration, I get an entire function here, some unknown function g of y. Because if I were to go backwards a step and differentiate all of this with respect to x, this entire function would be treated like a constant and it would go to 0. That's kind of what a constant of integration does when you check an antiderivative. So this is going to be my setup. Now, what is the function m of xy that we're actually dealing with? Well, it's x cubed plus y cubed. So I'm integrating x cubed plus y cubed with respect to x, and I'm getting also this extra plus gy showing up there. Integrating this with respect to x, this would become 1/4 x to the 4th plus xy cubed. Again, remember that y cubed is being treated like a constant, so its antiderivative would be xy cubed. Normally, again, I would be putting a plus c here, but I can think of that plus c as being incorporated into this unknown function here, so I don't need that really. Okay? So the function that we're looking for, f of xy, is this. But I can't use this because I don't know what g of y looks like. So I've got a somewhat of a picture of what the function f of xy looks like, but this little bit is still obscured to me. So how do we figure out what this term looks like? Well, notice so far I've only used m for my original differential equation. I'd like to see how n plays into that. So remember what n is. N is the partial of f with respect to y. That means if I differentiate this with respect to y, I can set it equal to n. Okay? So let's do that. This implies that n of xy is equal to, once again, the partial of f with respect to y, but that's equal to this thing differentiated with respect to y. This entire first term here only includes an x, so it's going to go to 0. This term right here, differentiated with respect to y, is equal to 3 xy squared. And then this second term here is going to look like g prime of y, because it's a single variable function and a differentiated with respect to y. But what is n of xy? Well, it comes from our differential equation up here. It's 3xy squared. So that means I have 3xy squared equals 3xy squared plus g prime of y. That would imply that g prime of y is equal to 0. Okay, but we know from calculus 1 that if a function has a derivative of 0, that means that the original function was a constant function. So g of y equals some constant c. That's what we can get out of that. All right, now what does all this tell us? Well, if I go back to my original function here, f of xy is equal to 1/4 x to the 4th plus xy cubed plus some constant c. Okay, now remember the whole point of doing this is because, again, if we take f of xy and set it equal to some arbitrary constant, that's going to be the implicit solution for this differential equation up here. So remember, I can take this entire expression, set it equal to some other constant, but then if I did that, I could take this constant and subtract it over, absorb it into that constant. And so this plus c here is actually pretty unnecessary because it's going to get absorbed into a different constant anyways. That means my solution to this dE is 1/4 x to the 4th plus xy cubed equals some constant c. Okay, and I can just call it done at that point, or if I prefer an explicit solution, I notice that this is one case where I actually can isolate the y. I would get y equals c minus 1/4 x to the 4th over x, and the whole thing I'm going to take a cube root of. So this would be an explicit solution. Either of these are acceptable unless I say, give me an explicit solution. But in most cases, if you can get an explicit solution, that's going to be the more preferable form. Okay? So this was among kind of the simpler examples of an exact equation. But notice we did two things. We started by checking that the equation was exact in the first place. Because if it wasn't exact, I wouldn't be able to do any of this, right? This would be a waste of time. So we want to know that we're working with an exact equation first. And that's very easy to check. It's a one-step thing. Then once you do that, you walk through this process. Now, if you have had Calculus 3, this process should feel very, very familiar. This is essentially the exact same thing that we do when checking to see if a vector field is conservative. If you haven't had Calculus 3, you're not going to know what I'm talking about there. But there is a direct relationship between these two things. If a differential equation is exact, then the vector field having these two functions as its component functions will be conservative, and vice versa. Not a theorem that we care about in this class, just a connection that you might be making if you've had Calc 3 already. Okay, I want to look at another example here. So this guy looks more complicated. Notice the differential equation that we're given is not in differential form yet. So I need to manipulate it. I need to change it into differential form. Now, I have a dy dt showing up here, so if I multiply everything by the differential dt, that's going to do what I need it to do. But not only am I going to do that, I'm going to simplify the expressions here and here that we're calling m and n, just to make the notation a tad easier. So simplifying this quotient right here, I'm going to get 3y to the negative third power minus t squared y to the negative fifth power, and that's going to be my dy, or that's going to be dy right there, plus Remember, you're multiplying everything by dt, but I'm also simplifying this expression a little bit. 1/2 t y to the negative 4th dt equals 0. Now we need to be really, really careful here, okay? Because, again, first of all, I'm using a t in place of an x, right? So in the previous example and in the derivation that we did, x was our independent variable. In addition to that, the functions that you're seeing here are in the reverse order of what we've seen already. If you go back to this previous differential equation, the function that was being multiplied to dx, x being my independent variable, was the first term of this equation here. And then the function being multiplied to my dy, where y is my dependent variable, shows up second. The dy is showing up first in this case instead of second. So what that actually means is that this is m and this is n. If you don't make that distinction, if you don't know to reverse the order in which these are appearing, you're going to get stuck. This problem is going to throw you for a loop. Okay. So with that said, what we want to do now is verify that we are in fact looking at an exact equation. So I take the partial of m with respect to y. Okay, remember we're only differentiating with respect to y, so if I did that, I'm going to get negative 2ty to the negative 5th power. Okay, now looking at n, remember we want to differentiate that with respect to x, or t in this case, because there is no x, it's t. If I differentiate this with respect to t, this entire first term is going to disappear. And then here, the y to the negative 5th is treated like a constant. I'm really just differentiating this. It's going to become negative 2ty to the negative 5th. Same thing. So this is my partial of n with respect to t. Okay? So that means that this is exact. And we're excited about it. So we put an exclamation point. Okay? So now that we know that, let's move forward with the same technique that we just did a second ago. And don't forget, in this case, we are looking at an IVP. So we want to go further than just get a family of solutions. But we still start the same way. All right. So let's see. Let's take... which function did I want to do before? Just looking over my notes here. I think I differentiated this guy. So... yeah. Oh, wait a second. I just want to make sure I'm doing this correctly. Okay, so let's take the function m here, just like before, and notice f of xy should equal the integral of m with respect to x, so m of xy dx plus... Oh, and you know what? Let me change that. It's not an x, is it? It's a t. Change those to t. And then we add some unknown function of y there. Okay? In this case, our function m looks like 1/2 ty to the negative 4th dt plus g of y. Integrating this, I'm going to get 1/4 t squared y to the negative 4th plus g of y. Again, remember, you don't need to do a constant of integration because it can be included in this. And that tells us what the form of f of xy is going to look like. Now, we want to compare this to n, my function up here. And I do that by differentiating this with respect to y, which would give me n. So n of x, y, is equal to the partial of this with respect to x, partial of f with respect to, y. And again, I'm making the same mistakes before. That's not an x, that's a t. This would be equal to, let's see, partial of this guy with respect to y would be negative t squared y to the negative 5th power plus g prime of y. Okay? This I want to compare to what I actually know n to look like, and we wrote n up here. So this implies that 3y to the negative third power minus t squared y to the negative fifth is equal to negative t squared y to the negative fifth plus g prime of y. Notice that these two terms match, so that means that these two terms must be equal. This means that g prime of y is equal to 3y to the negative third power. Find an antiderivative for that. That means g of y is equal to, what is g of y going to equal? It's going to be negative 3 halves y to the negative second power. Okay, and again, last time I wrote a plus c here, but remember that plus c ended up getting absorbed into the constant that we were going to use anyways. So what does this mean? This means that f of xy, which is given here, is equal to 1/4 t squared y to the negative fourth power plus g of y, which I just found. Let's actually call that minus 3 halves y to the negative second power. Okay, remember this thing we set equal to some arbitrary constant, and so now we have a solution, a general solution, 1/4 t squared y to the negative fourth minus 3 halves y to the negative 2, and I've noticed I did that again, didn't I? T. It's a hard habit for me to break. I'm seeing places where I'm putting x's, and I need to be putting t's there. Okay. Set this equal to c. This is a general solution to our dE, but we have more information than that. We have an initial condition, y of 1 equals 1, and so that needs to get substituted in here. That means both t and y are both equal to 1. So plugging in my initial condition, if I plug a 1 in for t and y, this term becomes 1/4. This term becomes minus 3 halves, and that equals c. This implies that c is equal to negative 5/4 after doing the subtraction. So my final answer is 1/4 t squared y to the negative fourth minus 3 halves y to the negative second power equals negative 5/4. That's my specific solution to this IVP. Now, this solution method naturally lends itself to implicit solutions like this. In the previous example, we were able to solve the implicit solution that we came up with, but the majority of the time you just can't. And that's why way back in chapter 1 we said that we'll oftentimes have to get an implicit solution. Sometimes an explicit solution is just too much to ask for. We have a little bit more to cover in this section. We'll knock that out in the next video.